So welcome everyone for this edition of the TCS Plus. Today we have Allan Sly. Allan Sly is an assistant professor in UC Berkeley. Previously he was a postdoc in MSR, Microsoft Research. And before that, he graduated from UC Berkeley under the supervision of Elhanan Mosul. His interests are mainly in mixing times of Markov chains, as well as phase transitions, and this will be the topic of today's talk. And let me just mention before we go around the table. Let me just mention the next few speakers. And we have in 2 weeks we have Madhusudan, and he'll be telling us about. See if I find it here. Yeah, he'll be telling us about communication with imperfectly shared randomness. And then the next talk will be by Shai Halevi from IBM Research about cryptographic schemes, recent developments, multilinear maps, and other exciting stuff. So maybe we quickly go around the table. Anidia, if you can start doing that. Thanks.
Thanks for that. So we have the group from Colombia. Let me actually present to everyone. Okay, good. Yeah, there's a group from Colombia. Then we have the group from Santa Fe. We have the group from MIT. I got them. There's a group from Paris. Okay, there's a group from Paris. We have a group from TTI Chicago. Well, Mother is here, so. We have Caltech. We have the group from UCSD. Okay. And we have the group from NYU. Excellent. So it's back to that.
Okay, thank you. Yeah, I forgot.
The assignments.
Yes. So
let
me
just biggest groups, I could see them being disappointed. So there's also a group from the Simons Institute.
Okay. So hi guys. Yeah. So also I forgot to thank. I forgot to thank Anidia and Thomas, who are both here with me today. They're helping run the operation, and also behind the scenes we have Thomas Hollenstein, Clément Canon, and Gautam Kamat. So I think that would be all, and let me welcome Allan again. Thank you, Allan, for agreeing to give the talk. So please go ahead, and if anyone has questions, please don't hesitate to interrupt and ask.
Yeah. Okay. Well, thank you very much for the invitation to speak in TCS Plus. I'm very excited about it. This is a semester where I'm teaching 2 classes, Monday, Wednesday, Friday. So it's can't really travel at all. So it's great to be able to give a talk to such a broad audience from the office. So I'll be talking about the satisfiability conjecture. This is. Is
there any way to? Very faint.
Hello.
Yeah, Mr. Verbet, please go ahead.
Oh, sorry. This is joint work with Zhan Ding and Nike Sun. So the random KSAT model is perhaps the canonical example of a random constraint satisfaction problem. So just just to describe the notation I'll be using, we'll think of n Boolean variables, x1 to xn, and a set of constraints or clauses that these will need to satisfy.
Alan, let me interrupt you. It seems some people report the volume is too low for them to hear. Is there any way you can speak louder? It's fine on my side, but maybe some people can go to the volume knob and crank it up.
Is this any better?
I
don't know. What do people say?
I can hear fine. Also, Alan, you need to switch off the presenter mode.
Yeah.
So that's fine. You don't need to switch on the presenter mode.
Yeah. So yes, I think we should try to go ahead. There's not much we can do about it. The microphone, Alan's microphone, is perhaps not the best, but I hope.
Sorry about that.
Yeah, we had some technical trouble here before. I hope, yeah, we'll just all be very quiet and try to listen carefully. I think it should work.
Okay, so we have a formula. Each of the clauses has n variables chosen uniformly. No, sorry, k variables for ksat chosen uniformly from the n possible choices, and with a random sign or literal. So, and we ask that all of the clauses be satisfied. And the question that we're interested in is how many clauses can you have such that you're still going to have solutions? So if we parameterize this by sort of alpha, the ratio of clauses to variables, how large can alpha be? Okay. It'll be really useful for this talk also to think about this in terms of a graphical representation. So encoding the ksat formula as a bipartite hypergraph. So if we took, say, this instance of 4sat, we could encode it as a bipartite graph as follows. So each of the variables corresponds to a vertex. Each of the clauses corresponds to a vertex. And we put an edge between a vertex, between a variable and a clause if that variable appears in the clause. So each of the clauses in this case will have degree 4, and I can also perhaps color the edges blue or yellow based on whether or not we have a plus or a minus literal. So this gives us sort of an ensemble of random graphs, and like most models of random graphs, it will be locally tree-like. If I pick one of the vertices of the graph at random and look at its local neighborhood, we won't see any small cycles. We'll just see a tree, and we can even say what the distribution of that should be. It should be given by some kind of a branching process. Okay. So it will be really useful for the talk to have this sort of graphical representation of ksat in mind. So the satisfiability conjecture says that we expect that there's a sharp threshold for the probability of being satisfied around some limiting value, which we'll call alpha sat. So just pictorially, if we looked at the probability of being satisfied as a function of n, it should get sharper and sharper, so converging to a step function around some limiting value alpha sat. So it's satisfiable with high probability for alpha less than alpha sat, and unsatisfiable with high probability when alpha is greater than alpha sat. So this is the conjecture. This is what I think everyone believes. It's been known for a very long time that it holds for k equals 2. There's you get sort of extra structure in that case, so that you can And so it was shown a long time ago, over 20 years ago, in fact, that it has a sharp threshold at alpha equals 1. For k greater than or equal to 3, though, it gets much more complicated. But in '99, Freegut proved a really landmark result, showing that SAT and other similar random constraint satisfaction problems have a sharp threshold. But it's a sharp threshold at some value which may be dependent on n. So really what's missing for the satisfiability threshold is to know that actually the threshold sequence is converging to some value, or that it really happens at some fixed, the transition really happens at some fixed point. Okay. And so the main theorem which I'll be talking about today is that we show that when k is sufficiently large, so bigger than some absolute constant k0, then we do indeed have this sharp threshold at a fixed value of alpha sat, and moreover, it's a value we can give a essentially explicit representation for, and it's one predicted. It's the value that statistical physicists predicted based on sort of very deep but non-rigorous heuristics, and I'll call it the one-step replica symmetry breaking prediction, and later on I'll explain a bit more about what that means. I'm gonna leave it to later in the talk to actually describe the location of the threshold. It's going to take a whole slide, and some extra background is useful before saying that. And at the end of the talk, I'm going to say a bit more about what happens when k is small and why we can't say things in that case. Okay, so that's the main result for today. Let me just review what was known previously. So if you just calculate the first moment of the number of solutions, you actually get a very good upper bound. It's within 1 of the right threshold. And if you do something a bit more sophisticated, like looking at locally maximal solutions, you can get an extremely good upper bound. So this has been known for quite a long time. So the main difficulty has been in proving good lower bounds. The first sort of ones of those were sort of more algorithmic in nature, but these are a long way away from the true threshold. And it seems quite plausible, at least, that this is because there may be no good algorithms for finding solutions to k-sat close to the threshold, and it may be that the result of Kodjo-Glan in 2010 is more or less the best possible algorithmic result you get, although of course we don't know whether or not that's the case. So all the other bounds, lower bounds on the satisfiability threshold, have been non-constructive. So and they've all relied on the second moment method, which I'll describe in a couple of slides' time. And so they've been progressively getting better and better until the best previous results were such that the gap between the upper and lower bounds, well, it was positive for every value of k, but the gap between them was tending to 0 as k goes to infinity. So really very, very close upper and lower bounds. So in this talk, the main result will be to get a gap of 0, to show matching upper and lower bounds, as long as k is sufficiently large. And the way we're going to do that is actually to prove separately.
I have a question.
Yeah.
So apart from the first two results, the other lower bounds are non-algorithmic in nature?
Yeah, all of those are non-algorithmic. Yeah, they're based on you know, just showing that the probability of having a solution is positive, and you can via the second moment method, which I'll talk about in a couple of slides. Yeah, so we don't, close to the threshold, there are no known algorithms that that seem to find solutions, even ones that we can't prove things about. Okay. So yeah, I've been saying moments are very important in this. So so let me talk a bit about that and what the challenges are in proving these results. So the most basic thing would be the first moment method. So to look at, say, Z, which we'll call the physicists would call the partition function, but you can just think of as the number of satisfying assignments to the K-SAT formula. We could just calculate its expected value. And it's very easy to write down exactly what that is, just by the probability that a particular assignment is satisfied. And this will be something that's either growing exponentially in n or shrinking exponentially in n. So the point at which the exponent is equal to 0 will give us an upper bound on the satisfiability threshold. It will separate the regime in which the expected value is going to infinity versus going to 0. But it doesn't give the right satisfiability threshold. Okay. To get a lower bound, the sort of natural thing to do is to try the second moment method. And the way the second moment method works is, what you want to do is show that the second moment of your random variable is of the same order as the first moment squared. And this, by some basic inequalities, shows that the probability that the random variable is positive is bounded away from 0. And if you know that, you can combine it with Freegutt's result to get a lower bound on the satisfiability threshold. Unfortunately, at least in its most basic application, this second moment condition fails, you know, for all densities alpha greater than 0. So you need to do something a bit more sophisticated. And I'll talk about in the next slide why that's failing. Okay. So there are essentially two reasons why the number of solutions is sort of not concentrated around its expected value, and they're distinct but also quite related. The first is what I'll call condensation, and what this is saying is that, well, the solutions are going to come in clusters, and the expected number of solutions will be dominated by sort of very rare atypical clusters, which don't usually come up in a typical instance of K-SAT, but is still enough to make the dominant contribution to the expected value. And this is only an issue when you're really close to the satisfiability threshold. A second issue, which is problematic at all values of alpha, is what we call neighborhood profile fluctuations. This is saying that we get sort of atypical types of graphs, ones perhaps where the degree distribution of the graph is wrong, and they give a dominant contribution to the expected value of the partition function. So in both of these cases, what happens is the expected value is going to be too large because of the contribution of very rare events, and so one needs to so overcoming these two difficulties is what one needs to do in order to use the second moment method. yeah, and so for the talk, I'll be explaining how we do this in order to get a sharp lower bound. I'll also I'll also talk a little bit about the upper bound, which is sort of much simpler and based on some other work. Okay, so let me now go on and talk about what's known from the statistical physics world and their picture of these models and sort of the insight that we get from that. Okay. So the genesis of the physicists' work on these models was really for models on dense graphs, and the canonical example of this was the spin glass models, particularly the Sharrington-Kirkpatrick model. Spin glasses are sort of I guess meant to be a model of like alloys of metals, and in a sense. So there was lots of work done by physicists on this, starting with Parisi in the late 70s, and in the last decade or so, many of these have been proved mathematically for these sort of dense graph models, ones where all of the variables interact with each other. But it's been noted by the physicists since at least the 80s that sort of random constraint satisfaction problems are sort of like sparse versions of these models, where variables only interact with a few of the other variables. Okay, so there's been a lot of work on developing a theory for random constraint satisfaction problems, models like KSAT, but also random colorings of random graphs, large independent sets of random graphs, not all equal SAT, and there are various others. And there's now a sort of very detailed picture of the behavior of these. And there's also been lots of work mathematically proving different aspects of these, different bounds. I'm not going to sort of really go through all the different results. I just want to talk about some of the key aspects in the physics picture that are important for proving the satisfiability threshold. Okay, so what the physicists say is that if you look at the geometry of the space of solutions, where you think of two solutions as being next to each other if they're just different at a single variable, is that there's a series of phase transitions. The first one is what you might call a clustering or shattering transition, where the space of solutions breaks up into exponentially many sort of well-separated small clusters of solutions. And this is probably, well, this may be the one that's most relevant from the algorithmic point of view of when you can find solutions. It sort of says local search algorithms are going to have a lot of trouble in this regime. But the next one along, the condensation threshold, is more relevant for today's talk in understanding when you get satisfiability, because it's one of the main sources of sort of non-concentration in a sense. And there are different ways we can think about this. One is what happens in the condensed phase is that rather than the distribution, or rather than the solutions being spread out over many clusters, most of the solutions are just in a small finite number of the clusters. But another way of thinking about it is in terms of sort of decomposing the expected partition function. So we could sum it up by summing over different cluster sizes and times the number of clusters of that size. You can certainly break up the sum like that, and you can imagine that there's some trade-off between having larger clusters and fewer of them, and so there should be a size of clusters which give the biggest contribution to this sum. What happens in the condensed region is that the size that gives the biggest contribution is a size for which clusters of that size are exponentially rare. So, so typically they won't come up, but because they're so big, they still have a big effect on the expected value. Okay. So in the last few years, there's been a lot of work on how to deal with this in improving bounds on constraint satisfaction problems. And basically the solution is, rather than trying to count the number of solutions, we should count the number of clusters of solutions. And in the next slide, I'll describe a bit about how you can go about that.
I have a question. So,
Yeah.
are these thresholds, the condensation threshold, is that like a well-defined quantity? Like satisfiability threshold, one can conjecture that whatever is the fraction of clauses at which the function is from satisfiable to non-satisfiable. Is it possible to rigorously define like what the condensation threshold is?
Yes. So one way you could do that is to look at sort of what's called the free energy, which would be like taking log of z and normalizing it by dividing by 1 on n. Mm-hmm. We'd expect this to converge to some value. Mm-hmm. And you get some function, so the free energy sort of encoding the exponential growth rate in the number of solutions. And this should converge to some function of alpha. And at the condensation threshold, you'll get a sort of point at which it's, you know, the second derivative doesn't exist. It's sort of not analytic at that point. So that's one way you can define it. There's also, you can also just write down a formula for where the physicists say it is. So it's
and are there conjectures saying that there are thresholds even for this condensation phase, or
so in fact, in the coloring model, which is quite closely related, Amin Kodroglon and a couple of his collaborators sort of were able to establish the existence of this phase transition in the sense of the free energy being not analytic at that point. Which is probably how a physicist would be their definition of this point. I mean, there are several things that can happen at that point, but that's one way you could define it. So each of these phase transitions, there's predictions as to sort of exact predictions as to where they should occur as well.
Okay, thanks.
Thanks for the question. So finally, this satisfiability threshold. Well, we can think of that as the point at which there are no more solutions, or also the point at which there are no more clusters of solutions, and that's going to be the sort of view that we take from here. Okay, so how do you deal with the condensation? Well, okay, I said at the beginning that the prediction was based on the one-step replica symmetry breaking heuristic. So there are various ways in interpreting what that actually means, but one sort of high-level picture of it is to say, okay, the solutions come in this sort of have a structure, they come in clusters, but once you look at the clusters themselves, there's no extra structure beyond that. So it's you only get one level of clustering. You don't, for instance, have clusters of clusters or some more complicated structure to the solutions. For other models, you do expect a more complicated structure. And what the heuristic suggests is that if you didn't have other sources of fluctuations coming from the neighborhood fluctuations, which I'll talk about later, if you just applied the second moment method to the number of clusters rather than the number of solutions, then that should give you the exact threshold. Okay. But the next issue would be, well, okay, how do we count the number of clusters? That's sort of I haven't really defined what they are, or I've just given you a picture of things. But there's actually a very straightforward way you can combinatorially represent a cluster, and that is by saying, well, if we imagine just a satisfying assignment being, I'll say, ones and zeros rather than pluses and minuses, sort of as being just all ones and zeros, we introduce a third possibility, which is that a variable is free. And what free will mean is not forced to take either the value 1 or 0 by any of its neighbors. So so all of the clauses it's in could be satisfied either with a 1 or a 0. And this description is essentially motivated by survey propagation. And it turns out essentially each cluster has a unique representation, more or less, in terms of this giving values of 1, 0, and free. So this is a sort of new combinatorial model that encodes clusters, and for which we can do computations of their first and second moments. And this has been how people have broken through the condensation threshold. So the first such result by Kodjo-Oglan and Panagiotou, they didn't use this sort of full representation of what clusters were, but they did a calculation which, in a sense, gave a sort of simpler proxy for it, and got the first result which got the first lower bound on the satisfiability threshold that beat the condensation threshold, in this case for the not all equal sat model. So last year in another TCS Plus talk, Zhan Ding talked about our work on the largest independent set for random regular graphs, and applying this sort of encoding of clusters. And because this is a random regular graph, being regular, there's no fluctuations in the neighborhood. Every vertex, the local neighborhood looks the same, just a regular tree. So in this case, the expected number of clusters exactly locates the threshold for the size of the largest independent set. You can give sort of you can calculate its asymptotic density in this way. And finally, Kodjo-Oglan and Panagiotou again applied this encoding to the KSAT model and got the previous best lower bound on the threshold. Essentially removed all of the non-concentration that comes from clustering, but that still left the non-concentration coming from the neighborhood profiles, which will be which I'll talk about in a little bit. Okay. So now I want to, having described that, talk about how one gets the upper bound on the satisfiability threshold. It comes from work coming from spin glasses and inequalities proved by Franz and Leone, and also Panchenko and Talleyrand. And Franz Leone in their paper actually commented that this would give the right upper bound for KSAT, although they didn't actually go through the details of that calculation. But so in some sense, the upper bound has been known for the last decade, although I'd say not very well known. And so what they show is they look at the sort of positive temperature version of SAT. So this is where, if you look, rather than saying, okay, we'll only look at assignments which are satisfied, we'll instead give them a weight according to e to the minus beta times the number of violated clauses. So you're penalizing it for each clause that gets violated. And so, so Franz and Leone give a formula for the free energy, the sort of limiting log partition function of this, and the formula, well, it's an infimum over mu, where mu ranges over Boolean exchangeable arrays. But what it's really representing is sort of possible joint distributions of a collection of randomly chosen vertices in the graph. And there's a functional p of mu, where what this is really, so there's a moderately complicated formula for it, but what it's really saying is it's calculating the effect of what if you added in an extra vertex to the graph? How would the number of solutions change? Okay, so they have this formula, but of course you don't know what the best value of mu is. But for our purposes, we only want an upper bound, and it's an infimum over mu. So we could plug in any value of mu that we like, and the optimal choice of mu is really suggested by the 1 RSB heuristics. Essentially, you want to know what is the marginal distribution of one of the variables in this 1, 0, and free model. And there are heuristics coming from the physics for how you should calculate that. It's there's sort of a recursive formula which actually will be on the next slide, and the point is essentially that it should be self-consistent in the sense that if you this marginal distribution for the vertices, if you add in a new vertex and connect it up with some clauses, that new vertex should have sort of the same kind of marginal as the other ones. So you want...
May I ask a question?
Go, please.
So is Franz Leone and Panchenko Telegrand, is this essentially saying that the bound is?
Sorry, I missed the last part of your question.
Is P sub beta the beta free energy per site? So they're basically saying the beta free energy is correct for positive temperature?
Yes. So it's, yeah, P sub beta would be you know, it's what you'd get if you so I mean it's sort of saying, well, if the neighboring vertices have distribution according to mu, then you add in a vertex and connect them up. This will be the change in the free energy, or the change in the log partition function as you go from, essentially as you go from n to n plus 1. It's sort of the usual sort of cavity equations, and so they prove this in the positive temperature version of the model. But you know, there's this somewhat complicated infimum over mu, and so they don't actually say what the right value of mu is there. But for our purposes, we can use this and make a guess of what the right value of mu is. I'm not sure if that was answering your question. So then if you, well, basically the story is then if you take beta going to infinity, you get the right upper bound. And it actually shows something a bit stronger than that. It shows that for any alpha greater than the satisfiability threshold, most assignments have, every assignment doesn't just violate one clause, it violates a linear number of the clauses. Okay. You can also use this to get bounds on, for any value of k. And so my student Yumeng Zhang looked at using this for 3-sat and could get an upper bound of about 4.28, which is sort of correct to about almost to the first 2 decimal points of the conjectured 3-sat threshold. It's an order of magnitude closer than the previous prediction. So actually this is so this gives a way of getting upper bounds in general. Okay, so that's based. So out of the 100 pages of the paper, the upper bound took about 2 of them. So almost all of the work is in the lower bound. Okay, and now let me also describe the explicit formula for the satisfiability threshold. So we have a recursion of probability measures, which we show converges to some limiting distribution mu alpha. And what this is representing essentially is that if you look at your k-sat instance, choose a random vertex, this will encode the distribution of the marginal distribution of it being a 1, say, in the 0, 1, and 3 encoding. Okay. And which will essentially be a function of its local neighborhood. So if you look at a vertex, you could sort of guess what's the probability of it being a 1 in a randomly chosen cluster, and you're a sort of good guess based on sort of, let's say, L levels of sort of its L level neighborhood would be to look at L levels of this recursion. Okay, so we have this distribution, and then we plug it into a function phi of alpha, which is meant to represent the free energy, so of the number of clusters of the model. So roughly speaking, this is saying that if we go from an n variable instance of k-sat to an n+1 variable instance, how much should the log of the number of clusters change? And so clearly we're interested in the point where the expected number of clusters goes from growing exponentially to shrinking exponentially. And so phi of alpha equals 0. The root of this equation is the 1 RSB prediction. So it's fairly explicit. It takes a surprisingly lot of work in order to actually just show that things like the recursion converges, phi is decreasing even as a function of alpha, but you can show that, and so this gives the prediction, and this is what we prove. Okay. So finally, let me talk about what was really the main work of the paper, which is taming the neighborhood profile fluctuations that we get, and their effect on non-concentration. So at the most basic level, you could think of a neighborhood profile as being like the degree profile of the graph. So for each vertex, we could look at its degree how many edges are coming out of it. And we could look at, or in a more complicated way, we could look at how many edges with plus literals and how many edges with minus literals it should have. And look at the empirical distribution of this over all of the vertices. And what you expect to get is that it should look like essentially a Poisson distribution. But of course, there's some randomness in it, and we'll get, so there'll be some fluctuations in this. And typically, there'll be like central limit theorem type fluctuations of order root n. So this would be the most basic example of what I mean by neighborhood fluctuations, say the number of vertices with a particular degree. Okay, but even this causes a problem. Imagine we want to calculate the expected number of clusters that we see. Well, we could break this up according to the different degree profiles that we see. So summing over degree profiles of their probability times the expected value. You can calculate each of these things pretty well. And for the probability of us seeing a particular degree profile, this will have sort of very simple large deviations behavior. It's easy to calculate what these are like. Unfortunately, if you look at the conditional expectation of the number of clusters given the degree profile, this isn't maximized at the typical profile. And worse than that, it's also non-stationary there. So in some directions, the derivative is positive. And if you combine those together, what you get is that the typical degree profiles are very much not a local maxima for this quantity. So very atypical degree profiles will make the dominant contribution to the expected value. And that's not what we want. That means that the expected number of clusters is not doesn't represent the typical number of clusters in the solution. Okay, so the first thing you might think of doing to correct for that is to condition on the number of, to condition on the degree sequence. But then I could say, okay, let's look at a more complicated neighborhood profile where we look at not just the degrees, that would be like depth 1, but we could look at the depth 2 neighborhood of each of the vertices. So these will be trees of depth 2. And if we condition on the depth 1 profile, then the conditional expectation will still be dominated by atypical depth 2 profiles, and so on. So, so just conditioning in a basic way isn't going to solve the problem.
Allan?
Yeah.
Can you give some intuition on why this is the case? Is it because like having lower degree makes more clusters or something?
Okay, so yeah, so at a basic level, it's because different vertices have sort of different marginal distributions in the graph. So you can imagine a vertex with lots of sort of plus literals in it is going to be more likely to be a plus. On the other hand, vertices that are sort of have very low degrees are sort of more likely to be okay. So imagine one sort of fluctuation you could imagine is you're adding a random clause. You're adding your random clause to the graph. If it's going into the dense part of the graph, which will be most of it, then that will sort of violate some of the clusters and sort of reduce the number of clusters by quite a lot. On the other hand, if it connected up to some of the very low degree vertices, then well if you have a cluster and if you add in a new clause and you connect it to a vertex, like a variable that's not in any clauses yet, that's not going to cause any problems because you can always fix that variable to be something to make sure that clause is okay. So different clauses will have sort of different different effects on the number of solutions and the number of clusters of solutions, and this sort of manifests itself in sort of the frequencies of different local neighborhoods. So, for instance, it would be better to have more vertices that are either have mainly plus literals or mainly minus literals, rather than ones that are sort of balanced between plus and minus literals, because they're sort of, you have to set it, because if it's say if it was all plus literals, you can always satisfy that variable by setting it to be a plus. And yeah, so really you need to so really these things only work if the second moment method will only work if all of the variables have the same marginal, or if you then do something sort of more complicated. Okay. So let me just describe the process we have for trying to deal with this. We work with neighborhoods around vertices of some depth r, and ultimately we'll take r to infinity, but you can think of that as being fixed. Then we remove the very worst vertices in the graph, but a fraction that's going to tend to 0 with r. So this gives us the remaining graph that we have left has some typical depth r neighborhood profile. We then okay. Now it's as I was sort of saying before, it's not enough just to condition on that. The way we can deal with that is by looking at a restricted set of clusters that have a certain marginal distribution, certain empirical distribution on their edges. And if we restrict to a sort of smaller class of clusters, then we will get a local maxima at the sort of typical neighborhood profile. And then after a sort of
another question.
Yeah.
So I thought the main problem was that if you, even if you're looking at like the level 2 neighborhood or something, there isn't enough concentration around the typical value. So is it the case that if you take R large enough, the second moment bounds will slowly start working? There will be concentration. Is that the point?
No, they'll actually never work. And yeah, so in order to make them work, we need to not look at all possible clusters that we could get, but look at clusters that satisfy an extra condition, which on the sort of so I guess to describe it would be essentially that the distribution for different edge types. We have edges from vertices to clauses, from variables to clauses, and the chance of that edge taking different values should, in a sense, depend on. We want it to not depend on the other variables in the clause when you look at the empirical distribution over the entire graph. Yeah, I'm not going to be able to describe that in a sort of fully precise way.
Okay. That's okay.
Okay.
Yeah, I mean, no, I was just wondering, like, so you somehow get rid of the these these atypical profiles which were causing the, so you somehow remove them and then look at the expectation, I mean, then look at the various statistics and they concentrate.
So
it's fine if it's hard to explain, it's fine. I mean, it's probably very difficult to explain this, so it's fine.
yeah, I'm probably not going to
Okay.
convey enough information about that.
Okay, let's go. Okay.
Okay, but after these steps, basically the second moment method will work. And so for each value of R, we'll get some lower bound on the satisfiability threshold. And we show that as we take R to infinity, this gives the right threshold. Okay. How much should I be wrapping up now, or how much?
I think we still have at least 5 minutes.
Okay. So let me say a bit about the different steps. So one of the biggest obstacles for this was that sort of had been skirted around in previous works that sort of could be avoided because they weren't getting right up to the threshold, was what to do with the sort of most rare difficult vertices. So let's say ones with very large degrees, so variables that are in a lot of clauses. And these cause a sort of big stumbling block in the optimization that you do for the second moment method. And since if we want to get all the way to the threshold, we can't remove too many of the variables, the graphs we have to deal with are sort of increasingly inhomogeneous. So basically the approach is to say, okay, we'll keep these very defective, rare, annoying variables, but only if they're surrounded by a lot of nice, normal-looking variables. And this really helps in the optimization process. Now, the full definition of which variables we keep and throw out is sort of more complicated and runs to about 3 pages, so I won't go through that in detail. In order to make the second moment to be stationary, we need to fix them up. Yeah. So this is what I was not explaining well before. We use a condition that was introduced by Kodjoglon and Panagiotou that says it's the clusters are judicious, and essentially it means that their empirical distribution satisfies certain equations that then sort of make the point stationary. The typical profile you get stationary. And then finally, most of the work is doing sort of essentially a combinatorial optimization problem in order to analyze the second moment and to show that most of the contribution comes from uncorrelated. So you can think of calculating the second moment as counting pairs of clusters, and you want to show that most of the contribution comes from essentially uncorrelated pairs. And by making all of the defective vertices be surrounded by nice variables, we get sort of it allows us to do this this optimization. And well, my favorite part of the proof, which I'm not going to say really anything about, is even though it's 36 pages long, is that we relate a sort of combinatorial optimization problem to a problem of looking at Gibbs measures on trees. And I guess I don't have time to say more about that. So let me just very quickly say what's the picture for small values of k, because this is a question people ask a lot. The glass half full picture is that all of the physicists say all the predictions should hold down to k equals 3. And there's no real reason why our program couldn't work, say, down to k equals 10, possibly even to k equals 3. That's, maybe that's being more optimistic. The glass half empty picture is that things are a lot easier when k is very large, essentially because everything, the degrees of vertices are very large, and so they're much more concentrated. Things become very spread out when k is small. So our result was in terms of a sort of some unknown lower bound of k0. In principle, one could go through the paper and make every lemma in the paper sort of give a quantitative version of that, and you'd get an explicit value for k0. We didn't have the energy for that. Okay, and yeah, but in principle, that's not really a problem to get some explicit value. Okay, and anyway, let me just finish there. So thanks for listening.
Okay, thank you, Allan.
Thanks, Allan.
So let's move on to some questions now. Questions, let's see. Berkeley Group, Chris, no. Allan, do you expect these techniques to apply to other problems now? Now that
yes. So for something like random colorings of random graphs, or you know, understanding when is an Erdős-Renyi random graph, say k colorable. The same overall program ought to work in that case as well, and yeah, and one could think of other sort of combinatorial problems on graphs for which you'd expect it to work. Another sort of thing which is a bit more complicated, but hopefully the machinery ought to be able to tackle is, say, the question of how many, when it's satisfiable, how many solutions you get. A harder sort of problem might be understanding what's the sort of value of the max cut in a random graph. That's sort of, the physicists would say that involves a more complicated type of replica symmetry breaking, where you get sort of your clusters are themselves made of you get clusters of clusters of clusters and so on like that. So that's probably a much further away goal.
any other questions? Okay, so if not, we'll turn the broadcast offline. Let me just remind you that